Let's take a look at the 2013 E&M problem number 1. This year they've given us a cylinder to take a look at, and fortunately they've been very kind to us and make the charge inside it of uniform volume density. Now it is uniform volume density because this is a non-conducting cylinder. That is a very important word that if you take a look all the way down here at part E, it will be replaced with a conducting cylinder. They're going to change the rules on us when we go from the first page of the problem to the second page of the problem. So pay attention to that. Notice that they've not given us numbers, so we're going to have to leave our answer in terms of the units, and we're going to use pi instead of 3.14 because we're not going to have any numbers for answers here unless, of course, the answer happens to be 0. All right, part A, using Gauss's law. That's very kind of them to give us a situation where we can use Gauss's law. If you notice, the squiggles here indicate that what we're seeing is just part of a very long cylinder. We're going to derive an expression. So derive here says you need to write down Gauss's law and show all your work. And we're going to be inside for part A. And then for part B, we're going to do the same thing, but we're going to be outside. And they want us to draw the appropriate Gaussian surface. Now remember I said that we were only going to deal with 3 shapes for electric fields and Gauss's law, cylinders being one of them. So let's draw a cylinder inside the other cylinder because that's where they told us to for part A. We're going inside. And we need to indicate that the axis of our Gaussian surface is the same axis as the actual physical cylinder that exists. The length is just representative and technically should be the same length, but all we care about is a representative length to show that this is a cylinder. All right, so for part A, showing the derivation, we need to start with Gauss's law. And in your class, we use the integral form of Gauss's law. And starting here, we will need to come up with an expression for Q enclosed to get rid of the Q enclosed, which we don't actually know, and put it in relation to the things that we do know. In this case, the thing that we do know is rho. And we can also figure out the volume based on the size of the cylinder. So Q enclosed divided by the volume enclosed is going to be the total charge over the total volume, total, but they didn't tell us the totals. What they told us was the uniform volume density is rho. So instead of using totals over totals, we will use rho. Now the volume enclosed is the volume of this smaller cylinder. So V enclosed is going to be pi r squared L. And we're going to use this when we take a look at the surface area of the cylinder. The surface area of the cylinder is the same thing as the derivative of the volume with respect to r. That's the surface area. So if we take the derivative of this expression here with respect to r, what we get is the circumference times the height of that cylinder. So we're going to substitute these guys into here. Notice we're going to have to multiply the volume enclosed by rho to get rid of Q enclosed. So we're going to have rho pi r squared L over epsilon naught, and substitute in for A times E on the other side. So the right side is going to be E 2 pi RL, and now we can cancel things out that appear on both sides. So let's get rid of the pi's and the L's and one of those R's and that R, and then we'll divide by 2. So our electric field becomes rho over 2 epsilon naught, and I'll put the R over here because the R is the variable thing and the rest of this stuff is a constant. And that's the end of part A. Part B. Derive an expression for when we're outside. So let's take all of the work from part A, and the only thing we're going to change is this V enclosed. Once you've enclosed all of the charge at the edge of the cylinder, stepping off the cylinder, you're not going to enclose any more charge because that's empty space. So if we make our new, and you don't need to do this on the actual test, but if we make our new Gaussian surface this guy, where that's still the radius of the Gaussians of the area that we're going to have. So the area is still going to be 2 pi little r L, but the charge stops at the boundary here, and it stops at this boundary here. So outside here, that's just empty space. There's no electrical charge there. So our volume enclosed is going to be pi big R squared L. I'll just leave this in a different color this time. So Q enclosed is going to be rho pi big R squared L. Our area is still going to be 2 pi little r L, because this describes the imaginary bubble that we've drawn. And when we plug these guys, when we substitute these guys into Gauss's law, and again, it does say use Gauss's law and derive, we're going to have rho pi r squared L over epsilon naught equals E 2 pi little r L. And once again, we will be canceling out things that show up in both places. Now, this time we're not canceling the r's because these are different r's. This r is the radius of the cylinder that contains the charge, and this r is the radius of the imaginary bubble that we drew around that. Solving for E gets us rho r squared over 2 epsilon naught, and now we have a 1 over r. Which brings us to part C. We're going to use both of these expressions, one from part A and the other one from part B, to sketch the function. Now, at r, so if we take a look at these two guys, when we set little r is equal to big R, so then we have rho big R over 2 epsilon naught. And if we do the same thing over here, set little r equal to big R, one of these r's now is going to cancel because that's a special case and they will be the same. And we have rho big R over 2 epsilon naught. At big R, those two expressions are the same. Inside, what we have is rho over 2 epsilon naught, that's a constant, and this is our variable. And what we have is y equals mx. This is just a line. And, oh boy. There we go. No, that's not where we go. Drawing lines on this thing is surprisingly difficult. There you go. That's supposed to be a line. And then on this side, we have rho big R squared over 2 epsilon naught, which is, again, a constant. And what we're going to have is C, and then our variable is 1 over R, which is 1 over X, which gets us an inverse curve. All right, let's get all this stuff out of the way, and we'll look at part D. All right, part D, expression of the magnitude of potential difference between R equals 0 and R equals big R. So D1, potential difference is going to be the negative integral of E dot dr. And what we're going to need is one of these two expressions. And since they say from 0 to R, what we need is the one that is the inside. What we need is this guy. This is the inside one. We don't need the outside. That's not relevant. So we're going to substitute this expression into here, and all we care about is the difference between these 2 points. So we can just plug in those 2 points as the limits of our integral. So from 0 to big R of rho over 2 epsilon naught R dr. And the rho and the 2 epsilon naught are constants, so they get to come up front. Well, I said it, and then I just started writing the same thing again. Let's try this again. So rho over 2 epsilon naught, 0 to big R, and we have R dr. Now this is r, and we never bother writing that 1 for the exponent, but the exponent will increase by 1, and we divide by our new exponent. So this will be minus rho over 2 epsilon naught r squared over 2, and then we will evaluate between 0 and r. And having done that, our lower limit, that's just 0 anyway, so we don't really care about that. And what you should notice is that the change in voltage, or the change in electric potential, starting at 0 and going to the radius r, gives us a negative as part of our answer. Which is relevant in part 2, where they ask which place is at a higher potential, r equals 0 or little r equals the big R. Well, since we have a negative here, and we were moving from 0 to r, this indicates that we went downhill. So since we went downhill, r equals 0 is at a higher potential. It's very nice that they didn't say justify your answer. I think the point is you've by doing part 1, you've justified your answer. So r equals 0. One more thing to keep in mind here, though, is that they asked for the magnitude of this. So since they asked the magnitude of that guy, let's move this out of the way. Not going to let me not select it. There we go. Since they asked for the magnitude of that, we should give them the magnitude, which is just the absolute value or the positive version. And this is, for part 1, this is where I would stop. All right, for part E, we're going to get rid of the non-conducting cylinder and replace it with a conducting cylinder. And what you need to remember about conducting cylinders is that the charge is always on the outside. And it doesn't matter if it's a solid or a hollow conducting cylinder, the charge will be on the outside. So what that means is, for our graph of the electric field, this E in, this rho is now going to be 0. This is just going to be 0. So since this is 0, 0 times anything is still 0, and our graph is going to be a horizontal line at 0. Then when we get to the boundary, right at the surface, we're going to now be dealing with the outside electric field that we had dealt with before, where this thing is now charge times length that we're dealing with. Or it should be surface area times length, not charge times length. It'll be charge divided by length. This is charge, and it'll be divided by length, but that's still constants. And we have our variable is 1 over r. So when we come here to make our graph, it jumps up to a maximum value right at the surface, but then it drops off as E is proportional to 1 over r, and inside E is equal to 0.